So hello students. So today we are going to learn some of the applications of our discussion on Markov chain, discrete Markov chain. Okay, and whatever we learned, say balance equations and the steady state probability. Okay, so let us start with this process called birth, death process. And then we will define specific kind of uh, birthday process is called queuing theory. Okay, later. So let me start with this. So for example, we are assuming that in a population there are like finite number of people are there. So we start with some state 0, and for each path it going to the higher state 1, 2, and so on. Okay, and then each date it is going to the lower state. So let me write down, say let's say bi is the probability that your random variable xn is taking value I plus 1 such that xn was I. So it's kind of a probability of path at n to n plus 1. Okay, so this you can write down that birth probability at state I. Okay, and similarly I'm defining, say di is the probability that xn plus 1 equal to I minus 1 given that xn equal to I, and this is you can write down as death di, so death probability probability at state I. Okay, so then let me draw this transition probability graph. So transition probability graph, how this will look like. So this will look like, say you start with state 0 and you go to state 1 after one bath, and then it is from 0 to 1 you are going, so this is v0. Okay, and from 1 to this is coming back by death, so this is d1. Okay, and then say 1 to 2, 2 to 1, and you can be at 1 also. Okay, there is no bath, no death at the same time. Okay, so this will be what? This will be b1, this is d2, but this will be, see, at 1 there are three possibilities: either there will be a path with probability b1, or there will be death probability d1, or it will be same. So it will be what? This is 1 minus b1 d1 is the probability that there will be neither path nor death. Similarly, at the 0th position you can have probability 1 minus v0 having no extra path. Okay, and so on dot dot dot. Now you recall that ith position and then I plus 1th position, what happened? So you have this and then this is general lowest position. So at position this will be vi, and then this is d I plus 1. Okay, and at this is here you have di this side. So this will be 1 minus, this probability will be 1 minus vi minus di, and then you have the image position, last position. Okay, at last position, so okay, let me write down m minus 1. So you have m minus 1 state, and then image image state. So you have this probability, and then you have this probability also, right? So this will be, so as usual, this is Bm minus 1, this is Dm, this is Dm, and this is 1 minus Dm, okay, and so on. So this is the transition probability graph will be of this form. Okay, so now we need to calculate this steady state probability, pi 1, pi 2, pi 1, pi 2, pi m. So how to calculate that? So you see that at each state, for example, at stage 0, state 0, what is happening? State 0, either you are having a path probability b0 or going to 1, or it will be remaining at 0, 1 with probability 1 minus b0, right? So then here, what will be this local balance equation? How it look like? Balance equation. So let me just do it at 0. So at 0, so this is I am defining by pi 0. So pi 0 will be look like what? So pi 0 will be um, um, see. So you can either go to you can either stay at 0 with probability 1 minus b0. So this probability, so it is 1 minus b0 times pi 0, or okay, or you can go to here with 1 with probability b0, right? So you can write down as sorry, or you can come to 0 from 1, okay, with probability d1. So it is write down d1 by 1. Okay, so at 0th position, either you can stay with probability this, or you can come from 1 to this 0 with probability 1, right? So in any case, you can write down this as pi 0 b0 by 0 is equal to d1 b0 by 0 equal to d1 by 1. Okay, so this is your, you can say, the first equation. Okay, now try to understand what happened at, so this is at state 0. Okay, now at state 1, what is happening? The steady state probability. Now you see that at 1, either you can come from 0 or you can come from 2, right? Or you can stay at 0. So steady state probability will be what? So pi 1 will be, if you come from 0 to 1, then it will be your pi 0 b0. If you stay at, come from 2 to 1, then it will be from 2 to 1 it is d2, so pi 2 d2, or you can stay at 1 with probability this, so this is pi 1 into 1 minus b1 d1, right? So this is coming from this balance equation. Okay, and now we already have this equation number 1, so you can substitute the value of equation number 1 here, pi 0 b0, and then it becomes pi 1 equal to d1 pi 1, and you see from here also you have a d1, so that get cancelled, right? So this is mine. Okay, so let me write down this d2 plus pi 1 minus b1 pi 1 minus d1 pi 1. So d1 pi 1 get cancelled and pi 1 both get cancelled, and finally what you get? So the answer is what is the final answer? The final answer is okay, so let me find out. Okay, so this is, so b1 pi 1 equal to d2 pi 2. So finally, so thus what you get? b1 pi 1 equal to d2 pi 2. Okay, this is equation number 2. Now you can assume that, so this is, you can understand the pattern, right? So so assume that ek position bk by k equal to same as dk plus 1 pi k plus 1. Okay, and then we need to go for the higher position, right? So we need to check for transition probabilities. See, this is a wanted position we find out. In kth position I assume it. Okay, so I am doing by induction, by mathematical induction. Right now at state k plus 1, what happened? So at state k plus 1, or I can assume at this is k minus 1, then it will be easier. So okay, so now this is, I'm assuming that for k minus 1 it is true, so I have to prove that at state k it is also true. Okay, so this is my, say, induction hypothesis. Okay, so now at k state, what do you have? We have from balance equation pi k will be, so there are three possibilities. Either it is coming from so I also am assuming that k is in between, say, m minus 1. So m is the total number of steps, right? M is connectors. Okay, so either it can come from k minus 1. So if you come from k minus 1, then what will the probability? So pi k minus 1 into when it's come from k minus 1, the probability is b k minus 1 into this. Okay, or it will be remaining at same. So this is 1 minus bk minus dk at pi k, or it can come from k plus 1, right? It can come from k plus 1 with the probability dk by k. Clear? So this is the balance equation, local valence equation at k. Okay, so if you local balance equation at k, then now you use that formula, that bk minus 1 pi k minus the star. Now using star, now using star, what do you get? So you get that pi k equal to okay, so 1 minute. Yeah, so what is, so this is the k plus 1, this k plus 1. Okay, coming from k plus 1. Okay, this k plus 1. Okay, now using star tells you that this is dk pi k, dk minus 1 pi k minus 1 dk pi k. So you use that, so pi will be dk pi k plus, from second equation you have 1 minus pi k. Okay, so that is pi k minus bk pi k. Bk pi k minus dk pi k. So bk pi k minus dk pi k, and last one is what? Dk plus 1 pi k plus 1. Okay, so this portion get cancelled, this one get cancelled, and pi get cancelled. So you have bk pi k equal to dk plus 1 pi k plus 1, right? So what does that mean? That means this equation is true. So this is true for all uh, this is true for all k equal to 1, 2 or 0, whatever. You can start with 0 also to m minus 1, right? So that's what you can get. So you can get that you can write down this as the k position is nothing but pi 0 times the recurrent relation gives you pi 0 times b0 b1 dot dot into b k minus 1, okay, and then d1 d2 dk, okay, and then is k equal to 1 2 and for m, right? That is okay. So from this equation, double star, from double star you are getting this. Okay, so now if you know and also you know another equation, that summation by k sum over k equal to 0 to say this equation is 1, right? So you already know that. Now using these two things you can easily find out these respective probabilities, right? So this is a general model. Now coming back to special model, is part of queuing theory. So okay, so you can also consider this birth date, but here what is the so here you have, so for example you can think that something is coming and something is going back, okay, like this, okay, and here I am assuming that it satisfy this kind of condition. So let me write down that this condition, okay, so so this process, so assume the following following um, conditions or following assumption, okay. So what are those assumptions? So that one new birth uh, happens, okay, so this is for happen in one discrete time, one period of time with probability so either this happens probability b, which is positive, so each discrete time either this happens or this happens, one existing um, person death happens, okay, with probability say d, death probability, okay, and or the third case, neither death or not any birth happened with probability, So no new death or birth happens with probability 1 minus b minus d if, okay, so this is if there is at least one person in the population, okay, or uh, if there is no person, so what does that mean? That if there is no population, there can be a death, but there can be path, right? So it can happen that, or no birth happens with probability say 1 minus b. So these are the conditions, okay, and I'm assuming that my state, so the state is state space says 0 1 2, so m is kind of finite, okay. Now we will see that what happens if m is very large or tends to infinity later. Let us first concentrate on finite case. Now under this case, whatever we discussed before, the path-based process, you see that our equation is this equation, right? Double star equation. Now here you see that all those bk's are b and dk's are d, right? So here, so all those bi's are b and di's are d, right? Then what happens? So thus the local balance equations become what happened? So this happens, b by I is nothing but d by I plus 1, right? And this for all I equal to 0 1 minus 1, right? Now let defining the symbol, say rho equal to b by d, the ratio of between path probability death probability. Then what happens if I use this symbol? Then my equation becomes we have uh, pi I plus 1 equal to rho times pi I, right? So this is my balance equation. Local balance equation become like this, okay. And we already know that the sum will be sum of such will be equal to 1, okay. So and also, yeah, so this is the kind of relation. So this implies pi I plus pi I, you see, you start with I plus 1, so you will have this. So what happened to the ith position? So pi I will be, so pi I will be rho times pi I minus 1, and then pi I minus 1 into times, so this is rho square times pi I minus 2 and so on. So finally the answer will be I times pi 0, right? Steady state probability at 0, okay. So pi I will be pi rho power I into pi I, right? And you already know the other equation. Other equation tells you that summation pi k equal to say 0 to m, this is 1. If we replace this equation by these values of pi I, then what will happen? Then you have summation k equal to 0 to m. So what will be pi k? Pi k equal to rho k times pi 0, which is 1, and thus you have pi 0 into this sum equal to 1. So 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 what is this sum? This is a geometric sum, right? Now hence okay, so I'm assuming here the case that rho not equal to 1, obviously. If rho equal to 1, then we know what. So if so see, rho not equal to 1, so this geometric sum, and then it will be nothing but so 1 minus rho over 1 minus rho power m plus 1. M plus 1 many times. This is if rho not equal to 1. But if rho equal to 1, then you have m plus 1 many terms. So this will be 1 by m plus 1, right? If rho equal to 1. So thus you will get that steady state probability at zero state is of this form, and hence you can find out all the probability, right? Because you know that now you know that the kth position, the probability is by k rho k into pi 0, and hence you can write down this as uh, pi power rho power k into 1 minus rho by 1 minus rho power m plus 1 if rho not equal to 1, and otherwise so otherwise pi, this is 1, right? M plus 1. Clear? So okay, so this formula gives you all the success probability, and you just understand this queuing theory process, how to do this queue process. Okay. Now you can observe. So remark. Now remark. So what happen if you consider, so let us consider m very large, that is so tending to 0, right? So like that is m tending to infinity. Okay. So then what are the cases? Then you have several cases. So case number 1. So now assume that, so first assumption is that suppose that b less than d, or d by d is low, so low less than 1, right? So what happened in this case? So in this case, this arrival, or I can say the path. So I'm writing arrival means uh, this path, okay, of a new object are less likely than departure. So departure means the death. So death. Okay. Departure of existing. Okay, and then what happened? So this prevents the. So then what happened? Then the steady state probability probabilities probabilities pi I decreases, right? with time I. Okay, so if you go, so you observe that. So why it is so? So start with this. So as m tends to infinity implies. So what will be this pi I? So pi I is uh, yeah, rho power I on one of this, and then when m tends to infinity, then pi I tends to rho power I 1 minus rho, because rho power m plus 1 tends to 0, right? Rho less than 1, so rho m tends to infinity gives this. So what does that mean? That means steady state probability are rho power I 1 minus rho, and rho is less than 1, so this is decreasing. Thus so this is a decreasing sequence. Okay, this is one case. Now, okay, and then you see that this has to be because you see that summation pi I when I equal to 0 to infinity, m tends to infinity, right? So this is nothing but summation rho power I 1 minus rho I equal to 0 to infinity, and you check that this is 1. Okay, this is 1. Clear? So this is one case, and second case. Now in second case, you assume that uh, then b greater than d or rho greater than 1. Okay, so if rho greater than 1, what happens? So in this case, uh, this arrivals or this north process, whatever, of new objects are more likely than departure, which is nothing but death of departures of existing packets. So what does that mean? That means the number of packets in the buffer tends to increase, right? Because there are more and more packets, so number of packets will be more and more and more and more that will be waiting, and then the steady state probability. So this pi I will be what? So pi I is rho power I 1 minus 0 by 1 minus, okay, m plus 1. So this is, see, because m tends to infinity, rho greater than 1, so this number tends to infinity, so this number tends to 0. Okay, so so for all I basically. Okay, so that means the steady state probability will decrease to 0, so it will be tends to 0. Okay, so this is the overall idea of this bath process. So and the Q process. Now we will give one more example here to understand this. steady state probability. So let us think this problem. So this is called that random walk, and you know what is random walk? We already discussed it before. Random walk with deflecting barriers. So what does that mean? So you know the meaning of random walk. So random walk means a person starts to somewhere, so he can go to either right side or left side with certain probabilities, right? Or you can come by something probabilities. Okay. So again, I'm assuming that so you have states so 1, 2, and say m. So you can go from 1 to 2 with probability say b, and come back with probability 1 minus b. And the moment you reach these intermediate states, the moment you reach 1 minus b, either 1 or m, and then you go to either next stage, right? So you cannot go to next stage, so then you need to return here, or you need to return here back. Clear? And this is you are coming to m with probability say b, here 1 minus b. Okay, so this is assumption that whenever you are reaching, say suppose the left side is 0, so from left side to right side, so you are going to left side means you are going to probability with 1 minus b, but you have a deflection, kind of mirror is there, you come back here. Similarly from m to m plus 1, if you are going, if you want to go there, you are going trying to go there right side, but you have a barrier, you come back here, so b. So this is the transition probability graph of this is the transition probability graph for this random walk with flexibility. Now one can ask what happened to this what happened to these probabilities, steady state probabilities. So for steady state probability, you can also again you can as it is a process similar almost. So you can find out the local balance equation. So the local, how the local balance equation look like. So you start with say at 0. So at 0 what is happening? Sorry, at 1. At 1 what is happening? So 1 either you can come from 2 or you can stay at 1, right? So pi 1 will be equal to 1 minus b of pi 1 plus, or you can come from okay, so at 1, right? So you can come from 2 to 1. Okay, so we put 1 minus b with pi 2 from 2, right? And then what is the meaning of this? So this means that b pi 1 equal to 1 minus b of pi 2. Clear? So this is at 1. Now at state 2, what is happening? Pi 2. So either you can so there is no chance that you will be staying at 2. Either you can come from 1 to 2 or 3 to 2, right? Now if you are coming from 1 to 2, so you are going to right side, so we call it b. So this is b 2 sorry, not b, b into pi 2 plus 1 minus b into pi 3, right? So sorry, uh, pi 1, b into pi 1, because from 1 you are coming. Okay, so 2 is what? So you are coming from 1 with probability b, or you are coming from 3 with probability 1 minus b, right? So this is pi 1 and pi 3, right? Okay. Now b pi 1 is nothing but 1 minus b into pi 2. So you can replace here. Pi 2 is nothing but 1 minus b pi 2 plus 1 minus b by 3, right? Now again you see pi 2 get cancelled and you get b by 2 is nothing but 1 minus b by 3. Okay, so you understand the model pattern. So in general, so now using mathematical induction, one can show that so homework, this for each I, so you can write down b pi I equal to 1 minus b into pi I plus 1 for I equal to 1 to m minus 1. Okay, you can show that. Okay, clear? So so let us write your rho equal to b over 1 minus b, and then we have, then what happened to local balance equation? So this becomes pi I plus 1 is rho pi I, right? For all I equal to 1 to m minus 1. Clear? So that is clear from this equation, and hence I can express thus. You can write down that for each I, pi I equal to power I minus 1 into pi 1 for all I equal to 1 to m, right? And again, what do you know? Again, you know that summation pi I equal to 1 to m, this is 1. So this implies summation rho power I minus 1 pi 1 I equal to 1 to m equal to 1, and you get pi 1 times geometry sum, right? So this is 1 plus rho square plus rho power m minus 1. This is 1, and geometry sum is so pi 1. So this is what? This is 1 minus rho power m by 1 minus rho, which is 1, and then pi 1 equal to 1 minus rho power. Okay, this is true. So this is true if rho not equal to 1. Okay, if rho not equal to 1, then so rho equal to 1 means what? B equal to half. So that is b not equal to half. Okay, and thus for any I, you can write down that pi minus 1 into 1 minus rho 1 minus rho power m, right? I equal to 1 to m and rho not equal to 1. Okay, so if rho equal to 1, what happens? If rho equal to 1, then you can find out that pi I equal to 1 by m, because you have m many places here, right? 1 1 1 on m many places, so this is m, and then it will be equal to this if rho equal to 1, that is b equal to half. Okay, so thus we understood that for random walk we will represent here. So that means I am talking about a random walk on finite state having this kind of steady state probability. Okay, so there are you can obviously do lots of other examples to understand these problems. Okay, maybe I will stop this here today, and my next lecture we will discuss about another interesting problem. We will use something called absorption probability, and using that we will study something called granular moving problem. Okay, so today we will stop here.